Hi guys, so today's video is going to be a review of everything that you need to know for the upcoming physics Regents. So I'm going to be reviewing all the units, and after each unit I'll do a few multiple choice questions just for some practice. And if you need more help on a specific unit, we have in-depth reviews on the channel, and it's all under the physics lessons playlist. So to lay the basics, you need to know kinematics. So you have to remember that a scalar quantity only counts magnitude, while a vector quantity counts both magnitude and direction. You guys should know velocity and acceleration, and remember that when an object is in free fall, that just means it's accelerating downward due to gravity. Also, these are the graphs that you should know at the bottom. So it's displacement of velocity and acceleration all over time. And these are the equations that you need to know. They're on the reference table if you need them. So let's do some practice for kinematics. Number 1, what is the average velocity of a car that travels 30 kilometers due west in 0.5 hour? So this first question is super easy. We just need to solve for velocity. You can find the equation on the reference table, but this should also kind of just be in your brain. So V equals D over T, and you just plug in. So it tells us the distance is 30 kilometers. So 30 kilometers over 0.5 hour. Put this in your calculator. It's going to be 60 kilometer per hour. But also, velocity is a vector quantity. So we need to include direction. It says it's going west, so it's going to be 60 kilometer per hour west. I'm going to skip number 2 because it's super easy. You're just solving for velocity again, so just plug it into the equation. Number 3. A ball is thrown horizontally with an initial velocity of 20 meters per second from the top of a tower 60 meters high. What is the horizontal velocity of the ball just before it reaches the ground? Okay, so we need to solve for horizontal velocity, right? So usually with one of these questions, you would write out all the information that you know and then plug it into a kinematic equation, but this one is a little bit different. So it tells us here that the initial horizontal velocity is 20 meters per second. So emphasis on the word horizontal. So for horizontal motion, basically VIX, so initial horizontal velocity is equal to final horizontal velocity, which is just equal to horizontal velocity in general, right? So that means horizontal velocity stays the same all throughout the entire motion. So this means that since the initial horizontal velocity was 20 meters per second, then the horizontal velocity right before it reaches the ground is also 20 meters per second. So the answer is choice C. Number 4, a ball is thrown straight downward with a speed of 0.5 meter per second from a height of 4 meters. What is the speed of the ball 0.7 second after it is released? So the ball is being thrown straight down, so we're working with the vertical component here. It tells us that the initial velocity is 0.5 meter per second, so I'm going to write that down. For kinematics equations, you should be writing down all the information that tells you so that you can plug it into the equation more easily. So VI equals 0.5 meter per second. Then it tells us that it travels from a height of 4 meters, so the distance is 4 meters. It tells us that it travels 0.7 second, so T equals 0.7 second. We need to find VF, and we know that acceleration is 9.81 meters per second squared because that's a constant. Now, we just plug all this info into an equation where we can solve for VF, so I'm going to use VF equals VI plus AT. So VF is equal to 0.5 meter per second plus 9.81 meters per second squared times 0.7 second. And then do the math for this, and you're going to get 7.4 meters per second. Number 5, a rock falls freely from rest near the surface of a planet where the acceleration due to gravity is 4 meters per second squared. What is the speed of this rock after it falls 32 meters? So we're going to do the same thing here. So it tells us that the rock falls from rest, keyword rest. So that means the initial velocity was 0. So VI equals 0. The acceleration in this situation isn't the usual 9.81, but they tell us that's 4. So we're going to use this value instead. So acceleration is equal to 4 meters per second squared. It tells us that it falls 32 meters, so the distance is 32 meters. And then we need to find VF. So in order to find VF, we can use the equation VF squared equals VI squared plus 2AD. So VF squared is equal to 0 plus 2 times 4 times 32 plug this in, solve it out, you're going to get 16. Okay, so now let's move on to Newton's laws. So Newton's first law is the law of inertia, which states that an object at rest will stay at rest and an object in motion will stay in motion. For example, if a puck is sliding on ice, it will slide forever if no external force acts upon it. The external force of friction is what eventually makes it stop. Also remember that inertia is just mass. Newton's second law is just net force is equal to mass times acceleration, which is a key equation which you need to know. And Newton's third law states that for every action, there's an equal and opposite reaction. So when you push on a wall, the wall will push that same force back onto you. Now, the diagram on the top right is a free body diagram. You should know how to draw one and how to identify the forces on one. Fg is gravitational force, which is the same thing as weight. Fn is normal force, so imagine this as the force that supports an object. Fa is applied force, and Ff is frictional force, which resists the motion of an object. Now, these are the equations that you need to know. They're pretty simple except for Fg parallel and Fg perpendicular. Basically, sometimes you'll need to split Fg into these two parts if the object is going on something like a ramp, but for the physics regions, it's pretty unlikely that you'll see this. So now let's do some examples. By the way, I'm taking these questions from random worksheets, so the numbers are kind of like all over the place, but don't pay any mind to that. So 15. Which graph best represents the motion of an object in equilibrium? So an object at equilibrium is either going to be at rest or at constant velocity. So obviously none of these graphs show an object at rest, so let's look for the one that shows constant velocity. So when an object is at constant velocity, its displacement is uniformly increasing over time. So it's going to be something like this, d over t, and it's going to be increasing like this. And then when this happens, the velocity is going to look like this, v over t, and it's going to be a straight line, straight horizontal line. And then the acceleration is going to look like this, a over t, and it's going to be at 0. There's going to be no acceleration if there's constant velocity. So let's look for the answer choice that shows one of these graphs. So the answer here is going to be C, because it shows displacement over time, and displacement is uniformly increasing over time, which results in constant velocity. 16. The diagram below shows a horizontal 12 Newton force being applied to two blocks, A and B, initially at rest on a horizontal frictionless surface. Block A has a mass of 1 kilogram and block B has a mass of 2 kilograms. The magnitude of the acceleration of block B is what? So we need to find acceleration, and we're given force and the mass of two objects that are being pushed together. With these values, we can use the equation F net equals ma and plug in to solve for acceleration. So F net is being told right here, so 12 newtons is equal to mass. So these two objects are being pushed together, so their masses are going to combine. So 2 plus 1 equals 3. So 3 kilograms times acceleration, plug in, acceleration is going to be 4 meters per second squared, which is answer choice D. 17. A 400 Newton girl standing on a dock exerts a force of 100 newtons on a 10,000 Newton sailboat as she pushes it away from the dock. How much force does a sailboat exert on the girl? Okay, so this is Newton's third law. For every action, there is an equal and opposite reaction. So the girl exerts a 100 Newton force on the sailboat, so the sailboat is going to exert a 100 Newton force back onto the girl. So the answer is choice B. 18. A 25 Newton horizontal force northward and a 35 Newton horizontal force southward act concurrently on a 15 kilogram object on a frictionless surface. What is the magnitude of the object's acceleration? Okay, so let's draw this out. There's a 15 kilogram object here, and there is a 25 Newton force acting on it north, and a 35 Newton force acting on it south. So these forces are unbalanced. So the south force is going to kind of like take over the northern force. So 35 newtons minus 25 newtons, that means there's going to be a 10 Newton force moving it south, right? So to find acceleration, we just once again use F net equals ma and then plug in, because now we know that the overall net force is 10 newtons south. So F net equals ma, so 10 newtons is equal to 15 kg times acceleration. Plug in, acceleration is going to equal 0.67. 19. A 750 Newton person stands in an elevator that is accelerating downward. The upward force of the elevator floor on the person must be what? So this person is 750 newtons and he needs to go downwards. If there's a 750 Newton force supporting his weight upwards, then he's just going to stand there at rest. He's not going to go down. That Fn supportive force needs to be less than 750 newtons in order for him to go downward. So the answer is going to be choice C. Moving on to the momentum unit. So momentum is represented as P, and it is an object's mass times velocity. Impulse is the change in momentum of an object, and there are a ton of ways to solve for impulse, so I wrote down all the equations for it. And a key concept is conservation of momentum. So the total momentum of a system will remain constant unless an external force acts on it. So a huge part of this unit is collisions. So basically you'll be given a bunch of scenarios where different objects collide and you'll need to solve for momentum. An elastic collision is when objects bounce off each other, and an inelastic collision is when objects stick to each other. They have different equations which we need to look at because these are not on the reference table. So for an elastic collision, the formula is m1v1i plus m2v2i equals m1v1f plus m2v2f. So this is basically just the momentum of the first object plus the momentum of the second object before the collision is equal to the momentum of the first plus the momentum of the second after the collision, since momentum stays the same. Now, for inelastic collisions, the formula is m1v1i plus m2v2i is equal to m1 plus m2 times vf. And this is because the masses of the objects combine when the objects stick together. So the last one is recoil. So for a recoil collision, the initial momentum is 0. So it's the same formula as elastic collisions, but just sub out all the initial stuff for 0. 32. The velocity time graph below represents the motion of a 3 kilogram cart along a straight line. The cart starts at t equals 0 and initially moves north. What is the magnitude of the change in momentum of the cart between t equals 0 and t equals 3 seconds? So remember that change in momentum is just impulse, right? So we need to solve for impulse, and we could do this through the equation impulse equals mass times change in velocity. And we're going between t equals 0 and t equals 3. So this is 0 and this is 3. So the change is 20 meters per second, because at time equals 0, it was at 0 meters per second, and at time equals 3, it was 20 meters per second. So J equals mass, 3 kilogram cart, so 3 kilograms times 20 meters per second, and that is an impulse of 60 kilograms times meters per second. 33. What is the momentum of a 1.5 times 10 to the third kilogram car as it travels 30 meters per second due east for 60 seconds? So it's just asking us for momentum. So the equation for momentum is P equals mv. So we just plug in. So P equals 1.5 times 10 to the third kilograms times 30 meters per second. And then we're going to get choice A. And remember to include the direction, and it says east. 34. Cart A has a mass of 2 kilograms and a speed of 3 meters per second. Cart B has a mass of 3 kilograms and a speed of 2 meters per second. Compared to the inertia and magnitude of momentum of Cart A, Cart B has what? So remember that inertia is just mass, and Cart B is 3 kilograms, while Cart A is only 2 kilograms. So Cart B has a greater inertia than Cart A. So that means choices A and C are going to be out. Now we have to compare their momentums. So remember, P equals mv. So both of these are going to end up being 3 because it's just 2 times 3 equals 6. Wait, what? Sorry. So both of their momentums are going to end up being 6. So that means they have the same momentum, but different inertias. So Cart B will have a greater inertia than Cart A, but they're going to have the same momentum. So that gives us choice B. 35. A cannonball with a mass of 1 kilogram is fired horizontally from a 500 kilogram cannon, initially at rest on a horizontal frictionless surface. The cannonball is acted on by an average force of 8 times 10 to the third newtons for 1 times 10 to the negative 1 second. What is the magnitude of the change in momentum of the cannonball during firing? So once again, change in momentum is just impulse. So we can use the formula J equals F net times t to solve for this. So F net, it tells us right here, average force of 8 times 10 to the third. So 8 times 10 to the third newtons. And time, 1 times 10 to the negative 1 second. And then do the math, and you're going to get choice B. 40. A 2 kilogram cart moving due east at 6 meters per second collides with a 3 kilogram cart moving due west. The carts stick together and come to rest after the collision. What was the initial speed of the 3 kilogram cart? So this is a collision, right? And it says the carts stick together, so this could be an inelastic collision where the carts stick together after they collide, right? So the formula for this is m1v1i plus m2v2i is equal to m1 plus m2 times vf. And we just plug in to solve. So m1v1. So the first cart is 2 kilograms times 6 meters per second plus the second cart, which is 3 kilograms. And we're trying to solve for this second velocity. And that's going to equal 2 kilograms plus 3 kilograms times VF, and it says they come to rest, so VF is going to be 0. So this is going to be basically 12 plus 3V equals 0. Finish doing the math, and you're going to get choice D, 4 meters per second. Okay, now moving on to centripetal motion. So centripetal motion is circular motion, and you need to know that the velocity of an object in centripetal motion is tangent to how the object is moving, but the acceleration of the object always goes towards the center, and centripetal acceleration is caused by the changing direction of the velocity. Now, you need to know the centripetal force, which is the force that keeps an object moving in a circular path. Centripetal force is represented as Fc, and centripetal acceleration is represented as AC, and these are the equations. Now, for this unit, we use big G, aka universal gravity constant, to find gravitational force, and all these equations can be found on the reference table. 33. A 2 times 10 to the third kilogram car travels at a constant speed of 12 meters per second around a circular curve of radius 30 meters. What is the magnitude of the centripetal acceleration of the car as it goes around the curve? So, let's look at the reference table for the centripetal acceleration formula and just plug in. So, the formula is AC equals V squared over R. So, V is 12 meters per second. So AC equals 12 squared, and the radius is 30. 12 squared over 30. Solve this out, and you're going to get 4.8 meters per second squared. 34. As a meteor moves from a distance of 16 Earth radii to a distance of 2 Earth radii from the center of Earth, the magnitude of the gravitational force between the meteor and Earth becomes what? So let's write out the formula for gravitational force. So Fg equals big G times mass 1 times mass 2 over r squared. Now, we can see that radius is in the denominator, so that means the relationship between radius and gravitational force are opposite. So as radius decreases, that means Fg is going to increase. So we can immediately eliminate choice A. Now, the radius goes from 16 to 2, and 16 divided by 2 is equal to 8. So the gravitational force should increase by 8 times, but radius is squared in this formula. So that means we have to do 8 squared, which equals 64. So that means the gravitational force will increase by 64 times. So that's choice C. 35. A car rounds a horizontal curve of constant radius at a constant speed. Which diagram best represents the directions of both the car's velocity v and acceleration a? So remember that velocity is tangent and acceleration goes towards the center, and this is shown in choice A. 36. Compared to the mass of an object at the surface of the Earth, the mass of the object a distance of 2 Earth radii from the center of the Earth is what? So mass is the same everywhere. If you're 50 kilograms on the surface of Earth, then you're still 50 kilograms, like 2 radii from Earth. It doesn't change, so the mass will be the same. 38. The diagram below shows a 5 kilogram bucket of water being swung in a horizontal circle of meter radius at a constant speed of 2 meters per second. The magnitude of the centripetal force on the bucket of water is approximately what? So once again, we just look at the reference table to find the centripetal force formula. So Fc is equal to mv squared over r, and we just plug in. So it tells us that the mass is 5 kilograms, and the velocity is 2, and the radius is 0.7. So we just plug this in, and we're going to get 29 newtons. Now let's move on to work, power, and energy. So work is the force which acts on an object to cause displacement. Power is the rate at which work is being done, and energy is the ability to do work. There are 3 types of energy which we solve for in this unit. Kinetic energy is the energy of motion, potential energy is stored energy, and elastic potential energy is the energy stored in a spring. Conservation of energy states that energy stays constant, but there will be situations in which you see energy decreasing, and this is because it's sometimes lost as heat. Now let's go over some key concepts for this unit. So there needs to be displacement for work to be done. Someone can travel 50 meters, but if they end up where they started, then no work has been done because there's no displacement. Additionally, force and displacement have to be going in the same direction for there to be work. For example, if I carry a box, I'm lifting the box using vertical force. If I move the box horizontally, that horizontal displacement means nothing because the force is vertical. So they're contradicting. Let's also quickly review pendulums. So a pendulum is the little swinging thing, and when a pendulum is at its highest point, potential energy is at its max, while there is zero kinetic energy. It's the opposite when the pendulum is at its lowest, as there will be no potential energy and max kinetic energy. And these are the equations that you need to know, and they're all in the reference table. 33. In the diagram below, 400 joules of work is done, raising a 72 Newton weight a vertical distance of 5 meters. How much work is done to overcome friction as the weight is raised? So it says that overall 400 joules of work is done, but we need to find out how much work was specifically done to combat friction or air resistance. So the formula for work is work equals FD. So it gives us force and distance, so we just plug in. So work is equal to force, 72 newtons. So 72 times distance, 5 meters. So work is going to equal 360. But it tells us that the total work done was 400 joules. So that means 400 minus 360 equals 40 newtons. So this 40 newtons was specifically done just to combat friction. So the answer is B. 34. A 15 kilogram mass is moving at 7.5 meters per second on a horizontal frictionless surface. What is the total work that must be done on the mass to increase its speed to 11.5 meters per second? So this question might seem a little confusing, but let's just think. So what formula in this unit has something about speed? That formula is kinetic energy. So we need to figure out how to relate this back to kinetic energy. So if you look at the reference table, it tells us that work is equal to total energy. So that means work is equal to energy. So to make things easier, I'm just going to solve for energy of the object. So formula for kinetic energy is Ke equals 1/2 mv squared. I'll just plug in for the scenario. So 1/2 times 15 kilograms times 7.5 meters per second squared, right? And that's going to equal 421. But it says that we need to increase its speed to 11.5 meters per second. So let me solve one more time. So 1/2 times 15 times 11.5 meters per second squared is going to equal 991. So if I just find the difference between these two numbers, I do 991 minus 421, that's going to equal 570 joules. So that means there needs to be 570 joules of work done in order to increase that speed. So the answer is choice C. 35. A shopping cart slows as it moves along a level floor. Which statement describes the energies of the cart? So the shopping cart is slowing down, which obviously means that's losing kinetic energy. So we can take out choices B and D. Now, it also talks about gravitational potential energy. So remember that gravitational potential energy is equal to mgh. So it only relates to mass, gravity, and height. So since it's moving along a level floor, that means the height stays constant, which means that the gravitational potential energy does not change. So the answer is going to be A. 38. The diagram represents a spring hanging vertically that stretches 0.05 meter when a 5 Newton block is attached. The spring block system is at rest in the position shown. The value of the spring constant is what? So we need to find spring constant, and we're given the amount that the spring is stretched, and we're given force. So we can use the equation Fs equals Kx. So force of the spring is 5 newtons. We're solving for K, which is spring constant, and we know X, which is 0.075 meter. Plug in, and you're going to get 67 Newton per meter. Now moving on to waves. So waves are disturbances that transfer energy from one place to another, but remember that they do not transfer matter. There are two types of waves, mechanical and electromagnetic. Mechanical waves travel through a medium, and there are two types, transverse and longitudinal. Transverse waves move perpendicular to wave direction, while longitudinal waves move parallel. For some reason, they always mention that sound waves are longitudinal, so try to remember that. The other type of wave is electromagnetic, which is a wave that can either travel through a medium or a vacuum. So let's quickly review the parts of a wave. So a wavelength is the length of one wave. Amplitude is the maximum displacement of a wave from its rest position. Frequency is the number of wavelengths that pass per second. And period is the amount of seconds for one wave to pass. So some key concepts. So interference is when two waves meet traveling along the same medium. Constructive interference is when the waves add up and result in a bigger amplitude. Destructive interference is when waves subtract and result in a smaller amplitude. Standing waves are when two identical waves meet, but they're traveling in different directions, so they make like this little pattern at the bottom. For standing waves, there are nodes and antinodes. A node is at zero displacement, while antinodes are at max displacement. Doppler effect is when a point source moves, so its frequency seems to change to a stationary observer despite being the same. So imagine a train is coming towards you. It's going to sound quiet when it's far away, but it's going to sound super loud when it's super close to you. So the actual volume of the train never changes, but it sounds different to the observer depending on its location. You should also know redshift and blue shift. So redshift is when the point source moves away, and blue shift is when the point source moves towards. Now, these are the formulas that you need to know, and they're pretty simple, and they're on the reference table. 27. Which wave diagram has both wavelength and amplitude labeled correctly? So remember, amplitude is max displacement of a wave from its rest position, and wavelength is just the length of a wave. So choice A is going to be correct here. So I like to count wavelength by going from A to E. So this is A, B, C, D, E. That's how I know that's correct. And amplitude is from rest to its max displacement. It's not going to be like this. That's too much. It's going to be like this. So that's why A is correct. 28. The diagram below shows two pulses, A and B, moving to the right along a uniform rope. Compared to pulse A, pulse B has what? So pulse A and pulse B are moving at the same speed. I know that because their arrows pretty much look the same. But pulse B is significantly higher, meaning that it has a larger amplitude, right? And amplitude is equal to energy. So since pulse B has a larger amplitude, that means it has more energy. So that means pulse B has the same speed but more energy. A transverse wave with an amplitude of 0.2 meter and a wavelength of 3 meters travels towards the right in a medium with a speed of 4 meters per second. On the diagram, place an X at each of 2 points that are in phase with each other. So basically, in-phase waves are just when the wave patterns match up with each other. So if you stack them on top of each other, they should look the same. So I'm just going to trace this, right? So that's one wave. I trace it. I'm going to move it. If I move it over here, see, it stacks perfectly. So I can say that this point is the same as this point. These 2 points are in phase with each other. 30. Calculate the period of the wave. So we need to solve for period. So let's write out the formula for period. So period is T equals 1 over F. So period equals 1 over frequency. But we don't know frequency. It does not tell us frequency here. So we need to solve for frequency. We can solve for frequency by doing V equals frequency times wavelength, because it tells us that the speed is 4 meters per second. So 4 meters per second equals frequency times wavelength, which is 3 meters. So 3 meters. So frequency is going to equal about 1.333. It goes on forever. So I just plug that in now. So T equals 1 over 1.333. and I'm going to get 0.75 second. So building off what we just learned with irregular waves, now we're going to focus on light waves. So light waves are electromagnetic, so they can also travel in a vacuum. Reflection is when light bounces off a surface and reflects, and there are two types of reflections. Regular reflection is when incident rays hit a smooth surface, so the reflected rays are parallel and a clear image forms. Diffuse reflection is when the incident rays hit a rough surface, so the reflected rays scatter and the image ends up all messed up. Now, refraction is when light bends as it goes to a different medium because of the change in speed. Index of refraction is the ratio between speed of light in a vacuum and speed of light in a material. Speed of light in a material changes, but speed of light in a vacuum is represented as c, and it's always 3 times 10 to the 8th meters per second. So a larger index of refraction means a denser medium, which results in light moving slower. And when light moves slower, the light ray will bend towards the normal line. When the index of refraction is lower, then the medium is less dense, so the light will move faster and the light ray will bend away from the normal line. Diffraction is when light waves bend around a barrier, so basically this is commonly known as double slit diffraction, where there's this barrier and 2 slits which the light comes through. The light comes through the slit and then spreads out, and when the light kind of overlaps, it causes these things called interference patterns. And these are the equations which you need to know, and once again, they are on the reference table. 31. A ray of monochromatic yellow light passes from water through flint glass and into medium X as shown below. The absolute index of refraction of medium X is what? Okay, so we're looking at indexes of refraction. We don't know the index of refraction for medium X, but the reference table tells us the indexes for water and flint glass. Water is 1.33 and flint glass is 1.66. Remember what I said before. Higher index of refraction means a denser medium, and a denser medium means that the light ray will bend towards the normal line. You can see this as the light ray goes from water to flint glass. It slightly bends towards the medium. Anyways, but if you look from flint glass to medium X, there's no change. It just keeps going straight. So that means that the index of refraction of medium X is the same as flint glass. So this is also going to be 1.66. So the answer is B. 32. The diagram below shows a ray of light being reflected from a plane mirror. Which letter indicates the angle of reflection? So remember, for reflection, this is going to be the angle of incidence, and this is going to be the angle of refraction. So it is C. Let's skip to 41. So a ray of light is traveling through a mineral sample that is submerged in water. The ray refracts as it enters the water as shown in the diagram below. Calculate the absolute index of refraction of the mineral. So we're given this little diagram and it shows us the light ray as it goes from the mineral sample to the water and it's refracting. We need to find the index of refraction of the mineral, and we can do this using the equation n1 sine theta 1 equals n2 sine theta 2. Remember, this is on your reference table. So we can just plug in. We need to solve for n1, but we know what sine theta 1 is. So sine theta 1 is going to be the first angle. So it's this, 27 equals n2. We know this because it's water, so 1.33. So 1.33 times sine theta 2. So sine 41. So solve this out, you're going to get an index of refraction of 1.92. Moving on to electrostatics. So remember the basics. So an electron is negative, a proton is positive, and a neutron is neutral. Same signs repel while opposite signs attract. So 2 electrons repel, but an electron and a proton attract. Induction is when a charged object is brought near a neutral object like an electroscope, and the electrons in the electroscope moved based on the charge of the charged object. So to simplify this, if I bring a negatively charged rod near the head of a neutral electroscope, all the electrons are going to move down towards the bottom of the electroscope away from the rod because same signs repel. Conduction is when a charged object makes direct contact with something and the electrons will physically transfer over to that object. Also, an electroscope is an instrument which detects electric charge. For this unit, you need to draw field lines, so know that field lines from a positive charge go outwards and the field lines from a negative charge go inwards. I remember this because, say, positive people like to give, so giving is going outwards, while negative people love to take, so they like to take inwards. So positive is out and negative is in. Also remember that the total charge of a system stays constant, but if multiple objects make contact, then their charges will just add up and then distribute evenly. Now, this is how you draw field lines. So if there's a positive and a negative charge, then those are attractive field lines. So you draw these lines straight towards each other, and as you move outwards, the lines start to curve. If there's two positives or two negatives, then those are repulsive field lines. So the lines will curve up and down away from each other, and the center makes like a diamond shape. If there are charged plates, then there's one negative plate and one positive plate. So in between the plates, you just draw straight lines, and outside the plates, you curve. And these are the electrostatics equations, which are on the reference table. 31. A positively charged rod is held near the knob of a neutral electroscope. Which diagram best represents the distribution of charge on the electroscope? So a positively held charged rod is being held near a neutral electroscope. Remember that opposite signs attract, so the electrons in this electroscope are going to be attracted to the positive rod. All the electrons will come rushing to the head of the electroscope, and all the protons will be pushed down towards the bottom, towards the leaves, right? So it's going to end up looking like choice B. See, negative and positive attract, and then positive and positive repel, which is why they're so far away. 32. In the diagram below, a cloth is brought near but does not touch a neutral electroscope. The electroscope leaves separate. What charge, if any, does the cloth have? So it's brought near but doesn't touch. So this is induction, not conduction. And we need to figure out the charge of the cloth. So let's not assume anything here because we don't know enough information. The cloth could be negative and all the electrons could be rushing towards the leaves away from the cloth. Or the cloth could be positive and all the protons are getting pushed into the leaves as the electrons go towards the cloth. So who knows? So the charge of the cloth is unknown. 33. Two oppositely charged parallel metal plates, 1 centimeter apart, exert a force with a magnitude of 3.6 times 10 to the negative 15 Newton on an electron placed between the plates. Calculate the magnitude of the electric field strength between the plates. So it tells us to solve for electric field strength. So all we need to do is go to the reference table and find the equation for electric field strength, which is E equals Fe over Q. It tells us electrostatic force right here, so we just plug in. So 3.6 times 10 to the negative 15 Newton over Q, which is charge. It tells us that we're using an electron here. So the charge of an electron is on the reference table. It's 1.6 times 10 to the negative 19th coulombs. So solve this out, you're going to get an electric field strength of 2.25 times 10 to the 4th newtons per coulombs. Okay, now on this diagram, we need to sketch at least 5 electric field lines to represent the field between two oppositely charged plates. So we have a negative plate and a positive plate. Remember, for positive charges, we're going outwards. And then for negative charges, we're going inwards. So same thing here. So we're going to draw straight lines in the middle. And it's going from positive to negative because positive gives and then negative takes. So this is how the arrows are going to point. And then when we go outwards like this, we're just going to curve. And this is perfect. Okay, so I never did a unit video on electric currents, but we can just briefly review that now. So electric current is represented as uppercase I, and it is the flow of electric charge. Voltage is potential energy difference, so it's what pushes electric current through a circuit. Resistance is how easy or difficult it is for current to flow, and a key equation that you need to know is Ohm's law, which is R equals V over I, or resistance equals voltage over current. So a circuit is a closed path where current flows, and it has a battery or a cell, resistors, and wires. A series circuit only has one path for current to flow through, and resistance in a series circuit adds up, voltage adds up, and current stays constant throughout the entire thing. A parallel circuit is a circuit with multiple current paths, and in a parallel circuit, resistance decreases as more resistors are added. So you calculate this by doing 1 over total resistance equals 1 over resistance 1, 1 over resistor 2, so on and so forth. Current adds up while voltage stays constant here. Now this is what a series circuit looks like, and this is what a parallel circuit looks like. Now these are the circuits equations that you need to know. I is current, and the unit for this is amps. R is resistance, the unit is ohms, and V is voltage, the unit is volts. This P looking thing is resistivity, Q is charge, and A is cross-sectional area. Also, a voltmeter measures volts, and an ammeter measures current. Number 1, a 12-volt battery is connected to resistors R1 and R2 as shown in the diagram below. If the reading of voltmeter V1 is 8 volts, what is the reading of voltmeter V2? So this is a series circuit, which means that the voltage adds up. So if the total voltage of the circuit is 12 volts and the first voltmeter reads 8 volts, then the other voltmeter has to add up to 12. So 12 volts minus 8 volts equals 4 volts. So this is 4 volts, which is choice D. Number 2, plastic insulation surrounds a wire having diameter D and length L as shown below. A decrease in the resistance of the wire would be produced by an increase in the what? So for this question, we need to look at the equation. Resistance equals resistivity times length over A. So if resistance is decreasing, then that can only mean one thing here. It would mean that A, which is cross-sectional area, is increasing because resistance is decreasing. See, since A is in the denominator, that means it would have that inverse relationship. So as A increases, that means R has to decrease. And remember, A is cross-sectional area, which is like the same thing as the diameter. So the answer is choice D, diameter D of the wire. Number 3, what is the current in ammeter A in the diagram below? So this is a parallel circuit, and we need to find the current in ammeter A. So at ammeter A, the resistance is 3 ohms, and the voltage is 9 volts, because the voltage in a parallel circuit stays the same all throughout. So now let's put this into the equation, R equals V over I. So resistance is 3 ohms, voltage is 9 volts, and we're trying to solve for I. So we solve this out, we're going to get 3 amps. Now I want to skip to question 6. So what is the current in the circuit represented in the diagram below? So now this is a simple series circuit. We need to find the current of the whole circuit here. So we know that voltage is 6, but we don't know the resistance yet because we have 3 resistors, but we don't have the total resistance. So for a series circuit, we just add up the resistors. So 1 plus 2 plus 3 is equal to 6 ohms. So the resistance of the entire circuit is 6 ohms. Now we can put this into R equals V over I. So 6 ohms equals 6 volts over I. I is going to equal 1 amp, which is choice A. Okay, so magnetism is a super easy unit. All you need to know is that there's a north pole and a south pole. The field lines will go from north to south. Like poles repel while unlike poles attract, and magnetic field is strongest where lines are closest. That's literally it. Number 1, 2 identical stationary bar magnets are arranged as shown in the diagram below. What is the direction of the magnetic field at point P? I tried to find a more complicated explanation for this, but this is literally the only way I can think to explain it. We're just going in between. Like, that's literally it. Like, the point is here, and then there's 2 bar magnets. Just go in between them. It's going to point in this direction. So that's why it's choice B. Number 2, the diagram below shows the lines of magnetic force between 2 north magnet poles. At which point is the magnetic field strength the greatest? So, like we said before, when the lines are closest, that's where the field strength is the greatest. So here at B, you can see that's super close to all the lines, so it's going to be point B. Number 3, charged particles can be accelerated by what? So the answer is going to be choice C, both in electric field and a magnetic field. That's kind of like common sense because we learned about, electrostatics and we learned about magnetism. Number 4, the diagram below represents lines of magnetic flux within a region of space. The magnetic field strength is greatest at point what? So once again, we're just looking for where it is the lines are most close together. That's going to be point B. So the answer is B. Finally, we have modern physics. So a key thing you need to know here is the photoelectric effect. So this is when light shines onto a metal surface and electrons are ejected from the surface. The ejected electrons are called photoelectrons. More light intensity means more photoelectrons, and higher frequency means higher energy of the photoelectrons. And threshold frequency is the minimum frequency for electrons to be emitted. So some key concepts that you need to know is wave-particle duality. So this is when waves can act like particles and particles can act like waves. You should know that photons are packets of light and that electrons occupy energy levels. And you either absorb or emit photons when changing these energy levels. The modern model for electrons is that they do not travel in fixed paths and they exist in fuzzy clouds. Also, this is all in the reference table, but you'll need to know like matter, hadrons, leptons, baryons, mesons, and quarks. But that's pretty easy. And these are the formulas that you need to know. 31. A moving alpha particle enters the space between two oppositely charged plates as indicated in the diagram below. Which arrow best represents the path of the alpha particle as it travels between the plates? So an alpha particle has a charge of +2. So this is a positive charge, right? Remember from electrostatics that positive and positive repel and positive and negative attract. So obviously this alpha particle is going to curve this way because it's attracted to the negative. So this is going to be B. 32. The strong force is the force of what? So I didn't talk about this in this video. I talked about this in the modern physics lessons video. But strong force is the force that keeps the protons and the neutrons together in a nucleus. So this is the attraction between nucleons. 33. Which phenomenon can only be explained by assuming that light is quantized? So when it says that light is quantized, this is basically just saying that light is existing in these packets of energy or these packets of light called photons. So which phenomenon kind of builds upon this? That's going to be photoelectric effect. Remember that photoelectric effect is saying that when light shines onto a metal surface, electrons are ejected, and those electrons are called photoelectrons. So this is going to be the photoelectric effect. 36. The graph below shows the maximum kinetic energy of photoelectrons ejected from a metal as a function of frequency of incident electromagnetic radiation. What is the work function of the metal? So if we look on the reference table, we can find the equation for work function. It's work function equals Planck's constant times threshold frequency. So we can see the threshold frequency right here. So this is where the graph starts. That's the minimum amount of energy that you need for photoelectrons to appear. So work function is equal to Planck's constant. Planck's constant is 6.63 times 10 to the negative 14. And then we multiply that by frequency. So 2 times 10 to the 15th. Solve this out and you're going to get 1.3 times 10 to the negative 18th joules. Okay, so I hope this video helps you guys. If you need specific help on a certain unit, we have unit videos that go way more in depth with a lot more practice. So I highly recommend checking those out. And good luck on the physics Regents.